All right, hey everybody. We've got another video here about Chapter 8, talking about special right triangles and trigonometry. Just like last week, if you run into trouble, email me. Let me know. I know this is a tricky section, but it is really important as we move forward to get just a basic handle on some basic concepts of trigonometry. There are pages posted from our textbook again, as well as answer keys, so you can practice after you watch this, check your work. Again, email me if you have questions. I'm happy to help. So we're going to start today talking about some special triangles. These are triangles that you covered in Algebra 1, so I'm hoping this is a review. Some 30, 60, 90 triangles and some 45, 45, 90 triangles. We're going to go from there and build on to our basic principles of trigonometry. So make sure we're paying attention. We're going to start today just by looking at a basic equilateral triangle, something we've worked a lot with. The things that we know about equilateral triangles is that all three angles are the same, 60 degrees. We also know that all three sides are the same. And for the sake of our example today, we're going to call each of those sides 2a. They could be anything, right? We just know that they're the same. What I want to do for our first example is cut this in half. So if I cut my equilateral triangle in half, I have bisected the base or side BC. I've also bisected the angle A, and I've created a right triangle, a perpendicular bisector. So we can now consider that angle 30 degrees. We can consider that section of BC as equal to A because it's cut in half, so it would be A on each side, right, equaling 2A. And you can now see why we use 2A for our side length, so that this is a nice, neat A. And if I chunk that piece off that we're not going to worry about today, I now have a 30, 60, 90 triangle. I know one of these is A and one of these is 2A. So this is kind of how this triangle was derived, how this was found originally when we, as mathematicians, came up with our rules for a 30, 60, 90 triangle. So if I wanted to do the work to figure out side AD, you probably remember from back when you first learned this, that this is going to be A times the square root of 3. Okay, that's where we should end up for this measurement, okay? But I want to show you why that works, okay? And the basic answer is the Pythagorean theorem, okay? So we've derived this 30, 60, 90 with a 2a as our hypotenuse and an a as one of our side lengths, and we're going to use those measurements with our Pythagorean theorem. So we know a squared plus b squared equals c squared. I'm going to call a side A just because it stops some confusion here. We're going to call this B, and then we're going to call this obviously C because that hypotenuse always has to be across from the right angle. So C squared would be 2A squared. All right, so now I have some simplifying to do over here. So this is going to end up being 4A squared. Over here, I've got a squared plus b squared. I'm going to subtract a squared from both sides because I want to get b alone so I can solve for it. And when I take a squared away from 4a squared, I just end up with 3a squared. To move ahead from here, I'm going to square root both sides. So b ends up all by itself. The square root of 3a squared, we could think about it as the square root of 3 times the square root of a squared, which will simplify to just be a plain a times that square root of 3. And you can see this now matches up with what we already knew from our basic rules was going to be true of a 30, 60, 90 triangle. So to pare all of that down, we basically just need to know that in any situation, the side that's across from the 30-degree angle is going to be A, or S, or X, or however you'd like to think of it. The side across from, let me change colors here, from the 60-degree angle is going to be A, or S, or X times the square root of 3. And the side that's across from our right angle, the hypotenuse, is always going to be equal to 2a or s or x or whatever you're using. If you can remember these rules, They will help you immensely when we get into working with these triangles. So if you need to, pause the video, get this diagram copied down so you have these measurements in your notes somewhere. All right, let's move on. Now we're going to look at a 45, 45, 90. In this situation, we know that the two angles are 45 degrees each. We also know that the two base legs are equal to each other. This is because they're both across from the exact same angle. So if we have a side across from a 45 degree angle and another side across from a 45 degree angle, they have to be the same length because those angles that are creating the side are the same. So our mystery side here is that hypotenuse. Again, we're going to use that Pythagorean theorem. So a squared plus b squared equals c squared. This is going to be side C. This will be A, this will be B. So I've got a squared plus a squared equals c squared. I can combine these to be 2a squared. And now when I simplify by square rooting both sides, I end up with c alone. This could be thought of as the square root of 2 times the square root of a squared, which simplifies to be a times the square root of 2. So in a 45, 45, 90 triangle, my legs are exactly the same measurement. My hypotenuse is the leg times the square root of 2. This is a little bit easier one, I think, but I also think it's important for us to see where those measurements come from, that we're not just making up these rules. So if you need, again, to pause and get this copied down in your notes, I would do that so we can use it later. All right, so let's take a look at an example. If I want to find these values or these missing pieces, we can use these rules to do that. So I know this is a right angle. I know this is 60 degrees, which just based on what I know about triangles tells me that this top angle is going to be 30. Now, we know based on our 30, 60, 90 rules that the side across from the 30 degree angle is always going to be equal to S or X or A, whatever we'd like it to be. All right, so I'm going to call that X. We know that the side across from our 60 degree angle is always equal to S, or we're using X for this, times the square root of 3. And finally, we always know that the side across from our right angle, or our hypotenuse, is equal to double that leg, or 2x. All right, so in this situation, we've got some things to figure out. We know x times the square root of 3 equals 15. Okay, that's the one that we're going to want to work with because it's the only one where we actually have some numbers to do something with. Over here, x is x. Here, 2x equals y. We can't solve there. But here, we can do some work. So to get x alone, I'm just going to divide both sides by the square root of 3. All right, now, if I use my calculator and I take 15 and I divide by the square root of 3, I end up with approximately 8.7. So that tells me x is equal to 8.7 feet. We already have this leg, it's 15. This other side we know is 2 times 8.7 is going to equal y. So if I take that times 2, I end up with about 17.4. So I've now been able to find all three sides of this triangle just using the rules that I've established. Now, if you wanted to, you could leave this in radical form and simplify your rationalize your denominator and simplify to give perfect answers. I'm okay if you just give rounded answers, just based on a decimal point. That's fine. All right, so that's kind of the 10-minute mark here. This is section 8.3. My goal today is to cover 8.3 and 8.4. So if you'd like to, you can stop the video here. You can go to the practice problems and you can do pages, I think it's 562 and 563 that I posted, and do some practice. Or you can move on, watch the second half of this video, and you can do all of the practice together. That's up to you. So this would be a good kind of halfway point if you want to go to 562 and 563 to get that practice in. Otherwise, we will keep on rolling. All right, so the first thing we need to know about section 8.4 is how to label the sides of the right triangles. And the first and most important thing we have to think about when we are labeling these sides is to remember that the hypotenuse is always going to be the hypotenuse. Okay, this side, in this case AC, the side that's across from our right angle, is always the hypotenuse. Its name will never change. So make sure that we don't get confused on that. It will never change. The second thing we need to remember is, there we go, that we're going to always be focusing on one angle. Okay? If we focus on A, then we'll have to think about other sides in relation to A. So in this situation, BC would be opposite of A. Okay, so if my focus is A, BC would be opposite of A. BA, because it touches that angle, is what we call adjacent. And AC, we always call the hypotenuse, right? That never changes. The hypotenuse is always the hypotenuse. So in looking at angle A, if that's our focus, BC is the opposite, AB is the adjacent, AC is the hypotenuse. That's reiterating what I said. AB is adjacent. But if we changed our focus, so we focused on C, how might those labels change? Well, if this is our focus now, hypotenuse is still always hypotenuse, but the opposite, or across from it, is AB now. Adjacent, meaning it's touching, if I could spell, that would be helpful. Adjacent is BC. So it all depends on that focus. It all depends on which angle we are focused on and thinking in relationship to. So if we focus on C, AB would be opposite, and BC would be adjacent. So we have to know these things if we're going to think about this next piece of our puzzle. And that is our special trigonometric ratios. We have kind of a funny acronym that we use to remember this. And that is thinking about, I guess we'll wait and give it to you at the end here, our three measurements. Okay, sine, cosine, and tangent. If I were you, I would pause this video and I would get these copied down. Now that you have these in your notes, we want to think about these as kind of this funny acronym. Okay, the sine is the opposite over the hypotenuse. So we call this SO. Sine is opposite over hypotenuse. The cosine is adjacent over hypotenuse. We call this CA. Cosine, adjacent, hypotenuse. And the final trigonometric ratio, tangent, is opposite over hypotenuse, which we call TOA. Tangent is opposite over hypotenuse. So as a whole, we call these ratios SOHCAHTOA. SOHCAHTOA, which is kind of a fun word. It's a word that sticks in your brain. I'm not sure why, but it always has. So when we think about SOHCAHTOA, so means the sine is opposite over hypotenuse. Ka means the cosine is adjacent over hypotenuse. TOA means tangent is opposite over adjacent. And this can help us remember just exactly how to find these ratios. So hopefully that helps you. Keep that in the back of your mind. All right. And we're going to look at an example. But before we do that, if your calculator looks like this, we're going to have to do a quick settings change before you can operate on these types of problems. If you have a different calculator than this, you might have to do a little Googling just to make sure that you have this. But when we work with trigonometry, we have to have our calculator in what we call degree mode. And so if this is your calculator, you're going to click this DRG button right here, and it's going to bring a menu up for you. And what you need to do is change your setting to be the DEG setting. Make sure that that's the one that's selected and press enter. My guess is right now it's on RAD for radian mode. We do not want radian mode for trigonometry. We want degree mode. Now, make sure you change this back when you're not doing trig. I'll write this out. Change it back. I have done this many times where I'll accidentally leave my calculator in the wrong mode, and I'll be getting all sorts of answers that are way off and way wrong. Okay, you won't be able to do trigonometry in radian mode, and you won't be able to do some of our regular algebra in degree mode. So make sure you have these kind of set aside and know which one is which. But degree mode is what we're going to need to operate with SOHCAHTOA. And you get there by hitting that DRG button, selecting the DEG or degree mode, and hitting enter, and you should be good to go. All right, so once you've done that, we can move on with our example today. All right, so the first thing I want to do, and if you want to follow along on this, I'm doing an example out of the book so that you can look at a little bit more detailed example. We're going to look at example 2 on, example 1 on page 569. 569. All right. So they have a nice triangle drawn there. It's labeled QRP. Ours is labeled ABC, and that's okay. I'll go ahead and change these to match that. So there, this is R. This is Q. I'll kind of turn that into a Q. And this is P. And their side RQ is 15. PQ is 17. And RP is 8. And they've done a couple examples, which is why I like this as a practice problem, just because it helps us to see all the different types of calculations we can do. So we're going to start with just finding the sine of P. Remember, SOHCAHTOA. SOHCAHTOA. So sine of P, sine is opposite over hypotenuse. So if I'm focused on P, my opposite is 15. My hypotenuse, which is always the hypotenuse, is 17. So we could list that as a fraction. We could turn it to a decimal, which is about 0.88-ish, somewhere in there. Okay? And you should find that that is our sine of angle P, 15 over 17. Now let's say I'm going to go to example letter E on that problem. E asks us for the cosine of Q. SOHCAHTOA, so cosine is adjacent. So here I'm focused on Q. My adjacent side is 15. My hypotenuse is always the hypotenuse, which is 17. You can see this is the exact same answer. So the sine of P was 15 over 17, and the cosine of Q was also 15 over 17, which is okay, because we're focused on different angles. We're focused on different measurements. That might happen, so don't get thrown off if that does happen. So the first section of your practice today is going to be doing just this, okay? Thinking about in terms of fractions and decimals, just opposite over hypotenuse, adjacent over hypotenuse, or opposite over adjacent. Okay, let's just do a quick tangent just for good measure. Let's say I wanted to find the tangent of P. opposite, 15, over adjacent, which is here, that is 8, 15 over 8. All right. So hopefully that's making some sense. Now, I want to take a second and think about how this might apply if I asked you for the the sine of r. Pause the video, think about this. If I wanted the sine of r, what measurements might I be looking at? So hopefully if you think about this a little bit, you'll realize we're looking for opposite over hypotenuse, right? Because SOHCAHTOA tells us sine is opposite over hypotenuse. The opposite of r across from it is 17. But the hypotenuse is always the hypotenuse, and it's also 17, which simplifies to 1. We know that angle r is 90 degrees. If you go on your calculator and you type in the sine of 90 degrees, you'll get 1. The sine of a 90-degree angle is 1. And that's why, because we have the opposite and the hypotenuse that are exactly the same. All right? So on the first part of your assignment, like I said, this is the kind of stuff that you'll be asked to look at. Now, I am going to challenge you a little bit today. Okay? There are some trickier ways that we can use SOHCAHTOA. All right, so take a look at this example, see if this makes some sense. So let's say that in this situation, I had the hypotenuse of 27. And let's say that I had a leg of 18. And I wanted to find angle A. Okay, now you can probably very easily tell me that, Mr. Withers, I'm dealing with the opposite side and I'm dealing with the hypotenuse. And SOHCAHTOA tells me that opposite over hypotenuse is sine. So the sine of measure A equals 18 over 27, or if I simplify that, I know that that's 2/3. So the sine of A equals 2/3. Okay, and that's great. That's the first part of your assignment today, is doing just that. Here's the issue. What if I want to figure out what angle A actually is? The good news is we have a way to do that. But the maybe not so good news is it's another set of rules that we have to think about. Now, the great part about these is they're not all that difficult to remember. All right, so we're going to take a look at those right now. We call these our inverse trigonometric ratios. Okay, so I'm just going to call these inverse trig ratios. All right, now inverse simply means doing our sine, our cosine, our tangent backwards. So if we know, this is what it says, if we know that the sine of A equals something, we'll call it x, then the inverse sine, and we show that as a -1 exponent, that means inverse, of x equals the measure of angle A. So if I know the sine of A equals x, if I take the inverse sine of x, that will tell me what A is. The same thing is true of any of our trig ratios. If the cosine of A equals x, then the inverse cosine of x equals angle A. If the tangent of A equals x, then the inverse tangent of x equals the measure of angle A. So all that we're being given here is the opportunity to work backwards and actually find out what our angles are. So using these ratios, we can do this. Now, how do you do an inverse trig ratio? Well, the good news is you can use your calculator, and I'm going to ask you to use that calculator. So I'm going to go back here. If you look really closely, up above our sine, cosine, and tangent buttons, there is a little blue font that has our inverse sine, inverse cosine, and inverse tangent. So you just hit second and then hit sine, and you're going to get inverse sine. Hit second cosine, and you'll get inverse cosine. Hit second tangent, and you'll get inverse tangent. So going back to our example, we had 27 and 18, and we're looking at the sine of A, and we said that that was opposite over hypotenuse, so 18 over 27. I think we had it all the way down to saying that the sine of A equals 2/3. Our inverse trig ratio tells us that if the sine of A equals that, then the inverse sine of 2/3 would equal angle A. So if I go into my calculator and I hit the inverse sine, so second sine, and I put in 2/3, we find that the measure of angle A is equal to 41.8. And we now know the angle measure of that angle in degrees. I don't want it to look like we're talking about C here, so I'll shorten up that circle. 41.8 degrees. So we could find that. Having that information is hugely beneficial because now we could find angle C, we could find the side of AB, we can do anything because we have an angle measure. Let's try another example. Let's say this time that I don't have a hypotenuse. Let's say that I have a leg of 6 and I have a leg of 20. And let's say that I want to find angle C. I need to think about, all right, we're finding the measure of angle C. I need to think about what sides I'm given. I don't have the hypotenuse. I have my opposite side and I have my adjacent side. So I think back to SOHCAHTOA, and I know I have opposite and I have adjacent, so I've got to use TOA. So the tangent of C equals opposite, which is 6, over adjacent, which is 20. I could simplify that, and I would find that the tangent of C equals 3 over 10. Now, using that inverse rule, if the tangent of C equals 3 over 10, then the inverse tangent of 3 over 10 must equal the measure of angle C. So if I go into my calculator and I find the inverse tangent, so I hit second, then I hit tangent, I put in 3/10, I find that the measure of angle C equals about 16.7 degrees. If you're not getting the same answers as me as you use your calculator for this, make sure you're in degree mode because that will make a difference. Hopefully this is making some sense. I'm going to stop the video now because it's getting kind of long. We're almost to 30 minutes now. If you have questions, email me. Khan Academy has some great resources on this. You can just Google trigonometric ratios and you're going to find plenty of information on this. Or rewind and watch these examples a couple times to make sure you got it down. There's also some great examples in your textbook and some practice problems. We're going to spend all of this week and next week on these. Okay, so don't freak out if you're having some trouble with this. It's okay. It's supposed to be tricky, but do your best. Ask me if you need help. And watch this video over again if you need to, or rewind it a couple minutes to see an example again to make sure we're getting some good practice and starting to understand trigonometric ratios. All right, best of luck this week. Stay healthy, stay safe, and we'll talk to you next week. Bye-bye.